In the last video, I described the human-induced climate change that we're seeing. However, I didn't really give you any lines of evidence. How do we know that stuff? So that's what this video is for. The big concept that we're going to cover in this lecture is that we have many lines of evidence to support human-caused global climate change. These lines of evidence show that overall we're going to have a general global warming trend and many other changes that we can expect. So what are those lines of evidence? The first one is our basic understanding of chemistry, physics, geology, and biology. This lets us predict what's going to happen if we change the composition of gases in the atmosphere, because we can take measurements on those different compositions and how they interact with sunlight or other factors to trap heat, right? So we can use our knowledge of these different topics to study the Earth as it currently is, to look at the Earth as it was, and use those to make predictions on what the Earth will become. We also have climate records. Those are found in tree rings, ice cores, and corals. So tree rings are going to be more short-term data. You might be able to find a tree that is 8,000 years old and look back in that record. But ice cores are going to be our long-term data. This is what an ice core looks like. They core down deep into a ice sheet, right? And so Antarctica is one of the best places to look because you have year-round ice sheets that aren't going to be melting. And so every year when it snows in Antarctica, that snow is fluffy and it traps little pockets of the current atmosphere within those snowflakes. And then more snow falls, and that snow gets compressed, and eventually it's going to become this solid ice. And within that ice, there are all of these trapped bubbles. So every year, you get a record of the atmospheric conditions that are trapped in these little bubbles from those years. So they can look at these ice cores, which I think the oldest one they had in Antarctica goes, almost 1 million years, 800,000 years. There's a newly discovered ice core that I believe is from somewhere, maybe it's also in Antarctica, but it's almost 3 million years old. So this is very long-term data on atmospheric conditions. And what they do is they look at the isotopes that are contained in those gases and use that to tell the temperature. So here is a graph of exactly that. So on the top, you have the CO2 concentration that we're following throughout these different years within that ice core. So you core down and you would have this record of the years. I can't remember how they measure from year to year, how that changes. That might have to do with like a radioactive isotope where it's going to be losing neutrons over time, and so maybe you could date it that way. But either way, they know what year it is as they're coring down, and as you take these little slices and you're looking inside those bubbles, and you look at the concentration of CO2 within each of those bubbles. Then what you do is for the ice in that layer, you look at the water that forms that ice and what ratio of isotopes it's made out of. So in colder years, you get less of the heavier isotopes of both hydrogen and oxygen. And so that's what this part of the graph represents. This %D, that's deuterium, it's a heavier form of hydrogen. So you can see every point that we have a peak in those heavy forms, we also have a peak in the CO2. And the reason why is that these heavier forms of hydrogen and oxygen appearing in these ice cores correspond with higher temperatures. And that's because heavier molecules of oxygen will form naturally, but to be evaporated out of the ocean at a higher rate, you need more energy because they're physically heavier. So to get more of those heavier forms evaporating out, you need hotter temperatures. So that causes more to evaporate out, and then they'll rain out first once you get to somewhere like the Arctic, right? So because they're heavier, they also fall out first and are more likely to be a higher percentage of the snow that's falling. So heavier isotopes are going to correspond with, or higher proportions of heavier isotopes are going to correspond with warmer years. And they know that because you can do those measurements now. So we take current data that we have now and we use it to infer what was happening in these earlier time periods where we don't have direct measurements. But we can look at the concentration of CO2 and we can look at the ratio of these heavier isotopes and use those to draw conclusions about the temperature. So everywhere where you see a spike here would also represent the temperature spiking. So that is the temperature proxy that we have. And throughout time, in our ice cores here, dating back 800,000 years, we see CO2 and temperature corresponding nicely to each other and remaining relatively stable, though they are isolating. Not isolating, oscillating. I am isolating. In addition to our historic records, we can also take direct measurements and observations in our current time. This is a graph of CO2 measurements from the atmosphere at the Mauna Loa Observatory, which I believe is in Hawaii. And if you look, the red line represents the actual measurements, right? And then the black line represents the smooth trend, so the average of those as we go. So if you think about what would be happening in our global sort of system, is that in the summertime, when the northern hemisphere is, so northern hemisphere summertime, when that's pointed more toward the sun, we get more photosynthesis happening. And the same would happen in the southern hemisphere when it's summertime there, is that they would have more photosynthesis, but those two don't balance each other out. So we don't have kind of a nice smooth trend overall. It oscillates because the northern hemisphere contains more land, right? And our boreal forests and just a larger mass of photosynthesizing plants are contained in that northern hemisphere. So in northern hemisphere summer, those would be points where we would have low CO2 concentrations every year because those plants are taking that CO2 out of the atmosphere. Then in northern hemisphere winter, a lot of those trees might lose their leaves or be frozen and dormant, and so we would get a spike in the CO2. And that happens every year very predictably. And so we can take that and just smooth it out and kind of take away that oscillation and see this overall trend of an increase in our CO2 concentrations every year. We can also measure other things that are not CO2. So we can measure how much water vapor is occurring in our atmosphere. We can look at the temperature in the troposphere. We can look at the state of our glaciers and ice sheets. Are they melting and decreasing in size, or are they expanding, having more freezing? What's our snow cover like? What's our surface temperature on land? How much heat is contained in our ocean? All of these measurements are measurements that we can take in different areas of the globe and compare them year to year and then over long periods of time to say what is happening trends-wise with our planet. And this last one is going to take all of these other three combined and put them into a model, so climate models. We have maybe our 10 indicators that would show us that warming is happening, right? And we'll take those measurements and we figured those out based on what we know about chemistry and physics and biology. And then we take each area of the globe and we map it out and we take those measurements from each of those areas and then we input them into our climate model. And maybe there's some areas that we can't get those measurements for, and so we either predict what those measurements might be for those areas or model it based on similar areas or like analogous places. So you would take all of that information, put it together, and then you would have the current state of the world and as things are. And then you take what we know about physics. If you were to add more CO2, you could say what that temperature change would be because we've seen those changes happen in the past. So you can model what would happen in the future to all of these other different factors. If you then just put into that model, what happens if we increase the CO2 this much? And so the way that they have modeled our current climate conditions, it is that increase in CO2 that is causing the majority of the changes that we're seeing. Those models line up nicely with the increase in CO2. This last one is fingerprint studies. So here we are trying to separate out causes and say, okay, let's attribute this particular change to this single cause. And this is going to be a broader example of a fingerprint study. So we are looking at different layers of the atmosphere. In particular, we're looking at the stratosphere and troposphere. The troposphere is the layer of the atmosphere closest to the Earth, and the stratosphere is just beyond that. So stratosphere is going to be closer to the sun and more influenced by what's going on in space. So here are some maps of changes in those two layers of the atmosphere and the temperature. So we're looking at degrees Celsius, and in the stratosphere, right, so lower stratosphere, there's overall a general trend of cooling, which we see spikes where it gets warmer in the stratosphere, and each of those corresponds to a volcanic eruption. So these dotted lines are volcanic eruptions. So that's because you're taking all of this hot ash and spewing it into the stratosphere, causing temporary warming, right? But overall, we have a trend of cooling in the stratosphere. But in the upper troposphere, we're seeing an overall trend of warming. So what that means is that if you were to argue, let's say, that sunspot cycles were causing the warming that we're seeing now, if that's because of increased input from sunlight, we should see more of that warming happening in the stratosphere than in the troposphere, right? Or at least to be in the same trend and have warming happening in both of those places. But if we're getting cooling in the lower stratosphere, that seems to indicate that the warming that we're experiencing must be occurring here, right, on the Earth's surface. Not so much as we're getting excess sunlight energy, but maybe we are trapping more of that sunlight energy somehow. Here's a page of links. I'll post these in the comments. These are great sources for understanding and learning about what's going on with climate right now. Most importantly, the reports from the IPCC are going to be a comprehensive source that is more or less apolitical, and I'll explain why in a second. So the IPCC is the Intergovernmental Panel on Climate Change. There's 195 different member countries and thousands of scientists that are contributing to this effort. So IPCC assessments are written by hundreds of leading scientists who then cooperate with hundreds of other experts. So we are collecting data, writing reports, and then thousands more experts are going to contribute by reading and reviewing those reports. This is a large-scale effort to collect all of the data about climate and make predictions about what's going to happen. And so the IPCC is providing information about what they think is going to happen based on this evidence, but they are not saying what we should do about it. So the important part there is that they're not taking a political stance. They're just giving the information to anybody and saying, this is what it is. You can now do something with it. The big conclusions from the most recent IPCC report were kind of based around this 1.5 degrees Celsius. So the Earth has already warmed about 1 degree Celsius, and we're increasing very slightly, but that's still a rapid rate if you think about the whole globe as a mean temperature. So we've already done 1 degree Celsius warming. So since 2000, the estimated level of human-induced warming has been equal to the level of observed warming, with a likely range of plus or minus 20%, accounting for uncertainty due to contributions from solar and volcanic activity over the historical period. And so they always report what their sort of confidence in the statements of the report are. And so this is a high confidence statement. There's a large amount of evidence that supports this. There's not a lot of error kind of in that evidence. So human-induced warming is the cause. 20 to 40% of the human population lives in regions that have already experienced warming of more than 1.5 degrees Celsius in at least one season. So that 1.5 degrees Celsius is an average for our globe, but it's going to be more severe in some places and less severe in others. If all anthropogenic emissions stopped immediately, we would see warming, but less or likely less than an additional 0.5 degrees Celsius. So if we went to net zero emissions right now, then we would still have warming because of some of the kind of cascades that have been put into place, some of the positive feedback loops that are operating already, but likely we wouldn't exceed this 1.5 degrees Celsius. The impacts of this warming will fall disproportionately on the poor and vulnerable. So global climate change is in every aspect a environmental justice issue, where the problems that and the hardships that will be faced by people from the changes that we're going to experience are going to fall disproportionately on poor people and ethnic minorities and vulnerable populations. And this was part of the findings of their report. There's no single answer to the question of whether it is feasible to limit warming to 1.5 degrees Celsius and adapt to the consequences. This is an interesting part of their conclusion, is that we can't say whether it's feasible or not. It depends on too many different interacting factors. And so that's kind of like the ball's in your court, right? What are you going to do about it? Because the rest of the findings of this, there's that if we kind of approach 1.5 degrees Celsius as an overall warming but don't exceed that point, then we can come back down from that and really limit the extreme impacts on many different aspects of our society. But if we surpass 1.5 degrees Celsius, particularly if we get up to 2, then we sort of hit this point where all of these extreme changes are going to be set into motion, and coming back from it will be very difficult. So the big goal now, based on these predictive models, is not to exceed 1.5 degrees Celsius. And to do that, in this report, they concluded that we would need to achieve net zero CO2 emissions globally by 2050. And so that means not that we're not producing CO2, but any CO2 that we produce, we are finding a way to absorb, right? How are we going to sequester that CO2 long term? And a great solution, as always, is trees.